So, welcome to the topic on kinematics. Okay. So, there will be total of 6 lectures on kinematics. Out of 6, the first 3 will cover mostly deformation gradient, polar decomposition and area and volume change. So, these topics will be covered in these 3 lectures, and we will try to do some numerical examples, okay, so that you get conversant with the idea, you know how to work with some numerical problem. Okay. So, following are the contents of today's lecture. We will start by introduction, followed by the idea of a continuum, that is what is meant by a continuum particle. This will be followed by description of motion of a deformable body, okay. And then we will look into 2 different descriptions used to describe the motion of the body, that is material and spatial configuration, spatial descriptions. Okay. Finally, we will see by what is the meaning of the term deformation gradient, and we will try to derive an expression for the deformation gradient. Okay. Now, so in continuum mechanics, we are mostly interested in change in shape, okay. That is deformation of bodies subjected to external loads. Okay. So, this external loads can be mechanical, they can be thermal, they can be some other kind of loads, okay. But in this course, we are only interested in mechanical loads. Okay. Now, before we can discuss the action of the forces, okay, which cause these deformation, it is necessary that we develop some understanding on how to characterize the deformation and how to quantify the deformation. Okay. So, characterize and quantify the deformation. Okay. So, the whole idea of next 6 lectures on kinematics is to develop measures, okay, which can characterize and quantify the deformation, okay, before we actually move on to the physical laws which govern the deformation. So, one of the very basic definition of kinematics is study of deformation without reference to the cause, okay, of such deformation. Okay. So, the cause of deformation is always some external load. Okay. Now, here in kinematics, we want to study the deformation, but without actually referring to the cause of the deformation, that is the external loads. Okay. Now, you remember that kinematics does not deal with prediction of deformation, but it deals with the development of measures which can describe all possible deformations which a continuum or a body can undergo. Okay. So, kinematics does not mean, okay, that you will be able to predict the deformation. Okay. So, here we are rather interested in development of certain measures, like measures for example, strain measures, which can describe all the possible deformations that a body can undergo. Okay. So, now next we will look into what is meant by a continuum particle. Okay. So, consider that you have this body. Okay. So, there is this body, yes. So, this body consists of volume B. Okay. So, now slowly we will introduce certain standard symbol which are often used in the terminology of continuum mechanics. They are pretty standard. So, we will be using the same as it is available in other book. So, this B, okay, this calligraphic B actually denotes the volume of the body, okay, and then partial B denotes the surface which bounds this body. Okay. Now, any body, okay, is represented by a continuous distribution of an infinite number of what is called a continuum particles. Okay. So, we assume in continuum mechanics that this body over here, okay, is made up of continuous distribution of infinite number of continuum particles. Okay. So, say we pick one point P. Okay. So, at the macroscopic scale, okay, at the scale where we can see the entire body. Okay. So, each continuum particle is a point, okay, say point P as it is shown in the figure. So, each continuum particle is a point of 0 extent, okay, just like a point on a scale, okay, or a ruler. When you draw a line and use the scale to mark a point, okay. So, point has no dimension. So, just like that, this continuum particle is a point of 0 extent, okay. It has no dimension. Okay. However, you should remember that a continuum particle is not a piece of material. Okay. It is not a piece of material. Okay. So, you can take say n number of these particles and you can assemble to get your volume B. Okay. It is not a piece of particle. So, there are an infinite such continuum particles which are present in the body at the macroscopic scale. Okay. However, when we actually zoom in this area, okay. So, when we go at the microscopic scale, okay. So, at the microscopic scale, the continuum particle can be thought of as something which derives its properties from a finite size region, okay, of dimension L. Okay. So, you have this region. Okay. So, the dimension of this region, it may be a sphere of diameter L. Okay. So, continuum particle derives its property as a average of all the properties of the atoms which are inside this region of say length L. Okay. So, the properties of the continuum particle is an average over the atomic behavior within this domain. Okay. So, anyway, all the objects or all the bodies are made up of atoms. Okay. So, you could guess that if I can somehow get the position and velocity of all the particles, all the atoms that are there in the body, then I can basically solve my system. That is all what I want to solve. But then even a centimeter cube of a body may contain somewhere close to 10 raised to the power 27 atoms. Okay. And it is not possible to solve for position and velocity of each such atom. So, there are for each atom there will be 6 unknowns. So, there will be 6 times the number of atoms, that many unknowns which are there, and it is nearly impossible. Okay. So, what we assume now is that the continuum particle, okay, shown here, will derive its property from the average of the atomic behavior of all the atoms which are there inside this domain. Okay. So, when you take this domain of length L, there will be many atoms present inside, and then any continuum property, okay, will be the average of the atomic behavior, okay, of all the atoms present inside this domain. Okay. So, as one moves from one particle to another continuum particle, these domains will overlap. So, once you move from one point P to another just neighboring point Q, so this domain will shift slightly, and most of the atoms which are there in one domain will be present in the another domain. So, as such, these domains will overlap. Okay. So, in this way you will get a continuous smooth field of continuum quantities. For example, stress and strain, okay, you will get a continuous smooth field. So, one of the fundamental assumption of continuum mechanics is that it is possible to define this length L. Okay. So, in continuum mechanics we assume that there is such length L, okay, which exists, okay, and then it is also assumed that the length L is large related to the atomic length scale. Okay. So, this length L is much larger than the atomic length scale, which means the size of an atom. Okay. This is much larger than the size of an atom. However, length L is smaller than the length scale associated with the variation of continuum quantities like stress and strain. Okay. So, when you see the scale at which the stress and strain are varying, for example, this length L will be much smaller than that length. Okay. So, this L is actually much bigger than the atomic length scale, but it is much smaller than the length scale at which the stress and strains will vary. Okay. So, when we talk about in the coming lectures about a point P, we are basically referring to a continuum particle P, okay, and this continuum particle P will actually derive all its property from a region of length L, okay, as a average over the atomic behavior of all the atoms which are present inside this domain L. Okay. So, once we have clarified, so later on when we are saying a point P, we actually will mean the continuum particle P. Okay. So, now let us consider how to define or characterize the motion of a deformable particle. Okay. Now, in continuum mechanics, we are dealing with bodies which are deformable. Okay. So, consider that you have a body. Okay. So, this is your body at time t equal to 0. Remember that in static problem, time t is a pseudo quantity. There is no such thing like actual time in a static problem. Okay. In dynamic problem, there is indeed a time, but in static problem, time is a pseudo quantity. So, let us say at time t equal to 0, that is when you start your observation of the system, okay, under the action of external forces. At time t, the body is occupying a volume B 0. Okay. Notice that we have put a subscript 0. Okay. So, that is a standard notation for volume in the configuration at time t equal to 0, and this volume is bounded by surface del B 0. Okay. So, there are some notations people, I will also make it clear that people also use, for example, omega, they may use V, okay, for denoting the volume. Okay. Similarly, for the surface they might use tau, they might use A, okay, like this, and they might use del sigma, okay, like this one may use, okay, but most commonly B and del B is usually used. Okay. Now, you have this body at time t equal to 0. Okay, let me rub this. Okay. And now, consider that the body is made of collection of material particles. Okay. So, these are material particles, okay. P is a material particle, okay, and the coordinate of each material particle is given by capital X. So, we have a subscript P here to denote that this coordinate X corresponds to point P, okay, or continuum particle at point P. Similarly, you have another continuum particle at Q, okay, or material particle at Q, and the coordinate of that is x q, capital X q at time t equal to 0, and these coordinates are with respect to basis, Cartesian basis x 1, x 2, x 3. Okay. So, let capital X 1, x 2, x 3 is the Cartesian basis at time t equal to 0. Okay. Now, once you apply the external forces, what will happen? The body will undergo shape change, volume change, okay, and will occupy, and it may actually move, and it may occupy some other configuration in space. Okay. Let us say at time t, the body is occupying a volume B bounded by del B. Notice we have not put any subscript. Okay. So, if there is no subscript, it means we are referring to the configuration at time t equal to t. Okay. Now, when the body deforms, okay, the point P will move, okay, and will occupy say small p in the configuration at time t. Similarly, Q will move, okay, say along the green line and occupy position Q. Okay. So, let us say x, small x p and small x q. Okay. I will come to it, what is small x and small x p and small x q. So, let us say the coordinate of points p and q are x p and x q at time t, okay, and say this is with respect to Cartesian basis small x 1, small x 2, small x 3 at time t. Now, what is usually assumed, there is no restriction that. So, what we have shown here in this figure, that both capital X and small x Cartesian basis they coincide, but it is not necessary that they always have to coincide, but for all practical purpose in this course we take those two to be coincident in this course. Okay. But for notational distinction, okay, we consider them apart. We use different notation for Cartesian basis at time t equal to 0 and Cartesian basis at time t. Okay. Now, the configuration at time t equal to 0, there are certain terms which are used. You can refer to the configuration at time t equal to 0 as initial configuration or the undeformed configuration or the reference configuration. Okay. So, these are some of the terms which are used for the configuration of the body at time t equal to 0. Okay. At time t, you refer to the configuration as either deformed configuration or current configuration. Okay. So, deformed means after the force is applied, the body has deformed and has occupied this particular position in space. Okay. Now, the motion, okay. So, the motion of particle p and q are represented here by these dotted red lines and green lines. Okay. So, the motion can be mathematically written as x equal to psi, psi is a function, okay, which is not known now, which is psi is a function of capital X comma t. So, it is a function of the initial position of the point and the current time t. Okay. So, this small x is called the current coordinate. Okay. So, the current coordinate, okay, is related to the initial coordinate x. Okay. So, capital X is called the initial coordinate, okay, and it is also a function of time, current time t. So, this relation x equal to psi of x comma t is called the deformation mapping, okay, or the it characterizes the motion of the body. Okay. So, if you see this red line, okay, and green line, these are representative of the motion of the particles at point P and Q. Okay. So, the way it is shown is, okay, so you do like this and write psi, okay, you write psi here. So, this means from time t equal to 0 to time t equal to t, the body has undergone a deformation given by mapping psi. Okay. So, our whole objective in continuum mechanics or finite element, to be very precise, is to get this mapping. Okay. We want to get this deformation mapping. If we know this mapping explicitly for any time t and for any particle initially at capital X at time t equal to 0, we can know its current position small x. Okay. So, that is our objective. Okay. So, we can write, for example, the position, current position of particle P, which is given by small x p, as psi of the initial position x p comma t, and the current position of point Q is psi of initial position x q comma t. Okay. So, you can just plug in the time t and the initial position of the particle and you can get its current position at time t. Okay. So, in finite deformation analysis, the displacement, okay, so these blue lines actually denote the displacement. Okay. So, the displacement in finite deformation analysis is given by u equal to final position x minus initial position capital X. Okay. So, this is the displacement. Okay. So, our whole objective, as I said, is to determine this deformation mapping. Okay. Now, in finite deformation analysis, we can use different descriptions, okay, to describe the continuum quantities. So, we will come across various continuum quantities like strains and stresses, and you can use different descriptions. Okay. So, one needs to make a distinction between the different descriptions, okay, and also establish the relation between them. Okay. So, we want to make a distinction between different descriptions that are used to describe the kinematic quantities, okay, or the continuum quantities in general, and also we want to relate these two, I mean these different descriptions. Okay. Say for example, density. Okay. You can express density in terms of where the body was before the deformation. Okay. So, the current density, say for example, you can express in terms of the body at time t equal to 0 or in the reference configuration, or you can also describe the density in terms of its current configuration, okay, that is where it is during the deformation. Okay. So, these are two different descriptions. Okay. So, the first one, okay. So, if the quantity is expressed in terms of where it was before the deformation, it is called as material description. Okay. So, what it means is, if you describe the current density in the configuration before the loads were applied, okay, say at time t equal to 0, then this kind of description will be called the material description. If a quantity is expressed in terms of where it is during the deformation, that is current configuration, okay, say current density is described in terms of current configuration, then it is called as, this kind of description is called as spatial description. Okay. So, you have two different kind of descriptions, you have material description and you have the spatial description to describe the continuum quantities. Okay. So, this material configuration is also sometimes called as the Lagrangian description, okay, and the spatial configuration is also called the Eulerian description. Okay. Now, but you should remember that the governing equations, okay, are always written in the current configuration, that is at time t equal to t, because that is where your equilibrium is achieved. Once you apply the forces, the body will deform and will be in equilibrium with the external forces at time t. So, your governing equations are always written in the current configuration, therefore, they are primarily formulated in the spatial configuration. Okay. So, in fluid mechanics, for example, one will work extensively in the spatial description, as the study of material particle is not of interest. Okay. So, in fluid mechanics, we will rather like to study what is happening at that particular point rather than following the particle itself. Okay. In solid mechanics, we almost exclusively work in the material description, okay, because in solid mechanics, we have at some point of time we have to write the constitutive relation, that is the relation between stresses and strain, okay, and this will involve material description. Okay. But it is not always that in solid mechanics problems you use material description. There is some problem like extrusion, where for certain reasons it is better to use the spatial description. Okay. You will rather like to point out your attention to a point in space. Okay. Now, in order to understand the difference between the material and spatial description, let us consider a simple scalar quantity like the current density rho. Okay. So, in material description, the variation of the density over the body can be described in terms of its position at time t equal to 0. Okay. So, the current density, this is density at time t, okay, at time t the body is occupying the configuration at t. Okay. So, this density is at time t, but I can express this density in terms of its initial position. Okay. So, this initial position is fixed, okay. It does not change with time. So, what it means is, what this statement actually means is, on the left hand side you have density, okay, at current time. On the right hand side you have a function of material coordinate. Okay. So, capital X is also called the material coordinate, small x is also called the spatial coordinate. So, density is function of material coordinates and current time. Since the material coordinate is fixed, okay, say you fix the material coordinate, okay. So, you have fixed the point at time t equal to 0, and as you vary the time t, what do you get? You get the density of the variation of density of the particle which was originally at capital X, at the material location capital X. Okay. So, you will always get the density, this relation will always give you the density of the material particle which was at capital X at t equal to 0. Okay. Now, in the spatial configuration, the current density would be expressed in terms of the current coordinates, okay, small x comma t. Okay. Now, if you fix x, okay, now if you fix x, you have focused your attention at a point in space, and as you vary time, what will happen? Because of this particular relation, because x is fixed, okay, and time is varying, what will happen? You will at a particular point in space, you will get different particles coming and occupying that position as the time varies. Okay. So, this density rho will give you the density at spatial position x as the time varies. Different particles will come and go, but the density at that point will be rho. So, in the spatial description, this equation will give you how the density varies at a spatial position, irrespective of what particle occupied that position. Okay. However, if you substitute the deformation mapping in this relation, what do you get? You will get rho equal to rho of psi x comma t comma t. If you use the deformation mapping, so this relation will be in principle same as this relation, they are both same then. Okay. So, this relation will actually give you the density at spatial position x, small x, of a material particle which was originally at capital X. Okay. So, as you can see in the material description, we are interested in say the density of a material particle. Okay. We are not interested in at a point in space, we are rather interested in the density of a material particle, how it varies, okay, for that particular particle. While in spatial description, we are usually interested in how the density varies at a spatial location, irrespective of which particle occupies that position. Okay. So, in spatial description, the interest is on spatial, the interest is on spatial location x. Okay. Now, coming to the topic of deformation gradient. Okay. Now, this deformation mapping that we had x equal to psi of capital X comma t, it only enables us to relate the position of points between the deformed and the undeformed configurations. Okay. So, if you have the deformation mapping, it will tell you how the current position is related to the its original position. Okay. The current position of a particle is related to the original position of the particle. Okay. So, that much you can know. However, the deformation mapping will not tell you anything about what happens in the immediate neighborhood of the point after the deformation. Okay. So, all you are getting is in the current, if the current coordinate of point x is spatial position is x, so its only original position was capital X, or if the original position was capital X at time t, its spatial position is small x. Okay. That is what you get, but what you are not getting is what is happening around the neighborhood of that point. Okay. Basically, you are not getting anything about the deformation. Okay. So, for defining strain and therefore deformation, we should be able to characterize the deformation around a point. Okay. So, if we want to define a strain, we want to define what happens to say a infinitesimal length dl around a particular point. Okay. So, strain is intuitively like change in length by original length. Okay. So, we want to, so length means we have to have 2 points. So, we want to, so if we want to define strain, we want to define what happens to the length between 2 points which are in the immediate neighborhood. Okay. So, if we can do that, we will be able to characterize the deformation. Okay. So, therefore, this we need what is called deformation gradient, and this deformation gradient enables us to characterize the deformation around a point. Okay. So, using deformation gradient, we will be able to characterize what is happening around a particular point. Okay. So, how the say length is changing or how the angle between two material lengths is changing. Okay. So, deformation gradient is central to the characterization of deformation of a body, and it is involved in all equations of kinematic quantities which quantify deformation. Okay. So, all kinematic quantities that will come across in next 6 lectures will have deformation gradient present somehow. Okay. And deformation gradient enables us to relate the spatial position of two neighboring points before and after the deformation. Okay. Now, again consider a body which is in its initial configuration or say reference configuration or the undeformed configuration at time t equal to 0. Okay. So, this is the configuration of the body at time t equal to 0. So, the volume is B 0 and is bounded by surface del B 0. Okay. Now, the body deforms. Okay. So, deformation mapping let us say is psi, and the body occupies this configuration at time t. Okay. Volume B and surface del B. Let us say we pick up a material particle at point P. The coordinate of this is capital X, and now say in the immediate neighborhood of P, we pick 2 points q1 which is at the distance of dx1. So, vector distance dx1, another point q2 of vector distance dx2. Now, we want to see what happens to these two vectors dx1 and dx2 after the deformation. Okay. Once this deformation happens, what happens to these two vectors pq1 and pq2. Okay. So, let us say P occupies position small p, okay, and its spatial coordinate is small x. Let us say q1 goes to small q1 and the vector pq1 is dx1, q2 goes to small q2 and vector pq2 is dx2. Okay. Now, using our usual expression for vectors, we know that the initial coordinate of point q1 given by x q1 can be written as x p, the coordinate of point P, plus the vector from P to q1. Okay. If you see this figure, this is your x q1. So, x q1 is nothing but x p plus x dx1. Okay. So, for purposefully we have not given the subscript p. Okay. but we can always write this as xp, okay, and this we can write as xp. Okay. So, at time t equal to 0, okay, at time t equal to 0, the position vector of point q1 is xp plus dx1. At time t equal to 0, the position vector of point q2 is xp plus dx2. Okay. So, this is very simple. So, then we can express the vector dx2 and dx1 in terms of the position of the points p, q2 and q1. Okay. So, dx2 will be x q2 minus xp and dx1 will be x q1 minus xp. Okay. So, what we are doing is just in equation 2 and 3 we are bringing xp on the other side. Okay. Now, because say we have the expression for deformation mapping, we can know the current spatial coordinates of points p, q1 and q2. So, the current spatial coordinate of point p given by xp is nothing but, in the deformation mapping you substitute the initial position of point p, which is capital xp, and you substitute time, the current time, you will get the current spatial coordinate of point p. Similarly, you can substitute the initial coordinates at time t equal to 0 of point q1 and q2, which is x q1 and x q2 in the deformation mapping, and you will be able to get the current coordinate or the spatial coordinates of point q1 and q2 given by x q1 and x q2. Okay. So, once we have this, okay, we can write the corresponding differential spatial vectors dx1, small dx1. Okay. If you see this figure over here, so this was your dx1. So, dx1 would be your, so this is your x q1. Okay. So, dx1 would be, so x q1 equal to xp plus dx1 and x q2 will be xp plus dx2. Okay. So, you can write dx1 as x q1 minus xp. Okay. So, difference of the spatial coordinates of point q1 and p. Now, the spatial coordinate of point q1 is nothing but x q1 of x q1 comma t minus the point, okay, of x p comma t. Okay. So, sometimes we write x, can also use psi here. Okay. We can write psi here. Okay. Now, x q1 is nothing but x p plus dx1. So, that is what we substitute. Okay. So, that is what we substitute here, and then we get this expression. So, dx1, the differential elemental spatial vector dx1 is psi function of xp plus dx1 comma t minus psi of xp comma t. Next, what we do is we use the Taylor series expansion and expand the first term on the right hand side. So, the first term will be, if you use Taylor series expansion, it will be psi of xp comma t plus del psi by del x evaluated at x1, okay, at the current, at the initial position x1, multiplied by original elemental differential material vector dx1 plus there will be higher order terms minus x psi of x p comma t. Now, both of these will go away, okay, and then you will be left with the second term plus some higher order term. Similarly, you can get an expression for dx2, okay, you can get the expression of dx2, okay. Again the first term and the last term will go away and you will have del psi by del x evaluated at x2 dx2 plus some higher order terms, okay. Now, we define our deformation gradient as del psi by del x. That is how we define the deformation gradient. That is how the deformation is varying at a particular location, okay, x. So, f is the symbol used for deformation gradient. So, capital F is more often than not is a symbol which is used for deformation gradient and is given by del psi by del x, okay, or we can always write this as del 0 psi, okay. So, del 0 means gradient with respect to the material coordinates, okay. So, del will actually mean gradient with respect to the spatial coordinate, that is the standard convention, okay. So, using this definition of deformation gradient, we can express our equations 9 and 10 as, and we neglect the higher order terms, they will be negligible, okay, because dx1 itself is very small. So, the square of all those will be even smaller quantities and we can just neglect and we can relate the elemental differential spatial vector dx1 to the elemental differential material vector dx1 through this relation. dx1 is f of dx1. Similarly, dx2 will be f of dx2, where this f here means the deformation gradient is evaluated at material position x1 and this f means deformation gradient is evaluated at material position x2, okay. So, in general we can express the deformation gradient sometimes as f equal to del x by capital X, okay. So, instead of writing del psi by del x given by equation 11, we will write del x by del capital X. This is also sometimes used, okay. So, here this x actually means a function, okay. It means this particular function which is nothing but same as our deformation mapping, okay. Now, so in indicial notation the deformation gradient will be written as double summation f I comma j e I tensor product E j, where small e I is the Cartesian basis for the description at time t and capital E is the Cartesian basis for the material description, that is configuration at time t equal to 0, okay. And f I j is one component of the deformation gradient, okay, and I and j are summed from 1 to 3. So, you notice that one of the indices is in the lower case, the other indices is in the upper case, because we use lower case indices for quantities in the spatial configuration and upper case indices for quantities in the material configuration or configuration at time t equal to 0. So, f I j is nothing but del x I by del x j, where both I and j go from 1 to 3. So, in total there are 9 components, okay, of deformation gradient. So, the inverse of a deformation gradient is defined as del x by del x or del of psi inverse, okay, and this is the initial notation of the inverse of the deformation gradient tensor, okay. So, you can show okay, and I will leave this as a proof. You can do it very easily, that the deformation gradient is a second order tensor. It is also called the deformation gradient tensor, and also deformation gradient tensor is a 2-point tensor. 2-point means it has certain components from one description or one configuration. There are certain components which are from another configuration. Okay. So, you can see here in equation 16, f I j was del x I by del x j. Okay. So, this x I is from the spatial configuration and capital X j is from the material configuration. So, there are two different configurations, hence the name 2-point tensor. So, a 2-point tensor relates quantities in two different configurations. Okay. So, therefore, f is not only a second order tensor, it is also a 2-point tensor. Okay. So, the first one I will leave as a exercise for you to do it yourself. It is very easy to show. You can start from any of the expression here given from 15 to 15 or 16, and you can use the fact that small x is a vector. Okay. So, you know the transformation relation for a vector, and you can show, okay, that deformation gradient is a second order tensor. Okay. Now, there are two other concepts which are used predominantly. One is called the push forward operation. Okay. So, push forward operation, when the relationship between the elemental material vector and the elemental spatial vector is defined by this particular relation, dx equal to phi star dx or explicitly f dx. So, this is called the push forward operation. You are, by using this operation, you are pushing the material vector in a way from time t equal to 0 to spatial vector at time t. Okay. So, this is like you are pushing d capital X to d small x. Okay. So, the notation used for push forward operation is phi star, and then there are the square brackets dx. So, square bracket does not mean multiplication, it means that the push forward takes the input dx and there is certain relation, that relation is f dx, and it will give you the push forward of d capital X, which is nothing but d small x. Similar to, as for example, there is push forward operation, there is something called pull back operation. Okay. So, if you take the inverse of push forward, so given the spatial vector dx, the pull back operation will give you the material vector dx. Okay. So, dx will be phi star inverse. So, notice we use -1 to denote the pull back. So, dx is phi star inverse dx or f inverse dx. Okay. So, from equation 16 you can see that if you multiply both side by f inverse, okay, and using the fact that f inverse f is identity, you can get this relation, that f inverse dx is d capital X. Okay. So, this is called a pull back. So, you have a spatial vector and you are pulling it back to the material configuration. Push forward is you have a material vector and you pushing it to the spatial configuration. Now, because the deformation gradient is a second order tensor, it can be expressed in terms of in a matrix form. Okay. And equation 19 shows you how it can be expressed in a matrix form. Okay. So the first, so it will be a 3 by 3 matrix. The first component will be F11, which is nothing but del x1 by del capital X1. F12 is nothing but del x1 by del capital X2. Okay. Similarly, you have F13, which is del x1 by del capital X3, so on, and finally, you have F33. Okay. So, this is F11, this is F12, this is F13, F33 is del capital X3 by del X3. Okay. So, where do you get x1, x2, x3? The spatial x1, x2, x3, that is obtained from the deformation mapping. So, you will know from the deformation mapping. Okay. So, you will be, so you basically have x equal to x of capital X comma t, or this is same as psi of x comma t, both means the same. So, this, so because x is a vector, it has 3 components. So, it has, so there are 3 equations here. You have x comma t, x3 is x3, x comma t. So, if you know these 3 equations, you can take the derivative of spatial coordinates x1, x2, x3 with respect to material coordinates capital X1, capital X2, capital X3 to get the deformation gradient. Okay. So, this completes our discussion on deformation gradient. Okay. So, next we will move to the definition of strain.